In this video, I introduce a preference transformer for reinforcement learning. Preference-based reinforcement learning provides a framework to train reinforcement learning agents by fitting human preferences into a real-world model that are applied to optimize the model policy for complex tasks. However, the traditional preference reinforcement learning requires a large amount of human feedback, which makes the model hard to scale up. Preference transformer is a transformer-based architecture, which takes a trajectory segment as input to extract task-relevant historical information. By stacking bidirectional and causal self-attention layers, preference transformer generates non-Markovian rewards and importance weights as output to match the human preference probability as shown here. There's a human preference by comparing two segments, sigma 0 and sigma 1. And then we use the two segments as the input to the real-world model to generate this preference probability. And then we use cross-entropy loss to train the model to fit the human preference into the real-world model. Humans compare two trajectory segments where sigma is a segment with a length h and y is a preference label. The preference label y is 1 indicates sigma 1 larger than sigma 0 and y is 0 indicates sigma 0 larger than sigma 1. Each triple is stored in dataset D to obtain a real-world function R caret parameterized by psi. A Markovian preference predictor is defined as here. The real-world function R caret is updated by minimizing the cross-entropy loss between the preference predictor and the actual human labels as shown here. And in this figure, we use various policies to generate trajectories, and then human labelers generate this set of comparisons. And then we use each comparison to fit to the real-world model. And then we train the model to fit the human preference to the real-world model. The policy is updated using any reinforcement learning algorithm such that it maximizes the expected returns with respect to the learned reward. Preference transformer outputting probability of preferring a segment depends exponentially on the weighted sum of non-Markovian rewards, as shown here. The non-Markovian reward function R caret receives the four preceding subtrajectory as inputs. The reward importance weights W, a function of the entire trajectory segment, which performs the credit assignment within the segment. Preference transformer consists of causal transformer and preference attention layer. In given trajectory segment sigma of length h, causal transformer takes as an input 2h embeddings for state and action. State and action at the same time step share the same position embedding in the transformer. The causal transformer produces output embeddings x t such that the output at time t depends on input embedding from the beginning to the current time t. Preference attention layer maps the hidden embeddings xt from the causal transformer to real-world R caret and importance weights wt. The input xt is mapped to a key kt, query qt, and the value rt caret. During training, state action pairs are used to approximate the real-world rt caret. The output zi is defined as a context combination of values with attention weights from query and key as shown here. The weighted sum of a reward is computed by the average of the output Z A I as shown here, or where WT is calculated from this formulation as shown here. This preference transform that consists of causal transformer and preference attention layer. Here is a detailed causal transformer structure, and this is the preference attention structure. For more details, please check with these references. Thank you. Bye.